Okay, so in the last section, we were talking about the rectangles, and you recognize that there was a lot of room for error, right? Because those rectangles, when you flatten out the top, there is a lot that's open, okay? So what we're going to do here is we're going to review, we're going to, instead of making it rectangles, we're going to see if there is another shape. And you can already tell this is going to be a trapezoid, right? So let's take a look for a minute. Suppose I were to, divide this into, this many subdivisions. Okay? Let me make it more. Okay, now, one other thing I could do is I can make these not rectangles, but trapezoids. So look, if I make this one a rectangle, that's what it looks like. And then you've got that triangle up there that's being underestimated. But if I make that a trapezoid instead, now look at how it looks. Like, do you see how much of a better approximation that is, right? And I can make that a trapezoid and that a trapezoid, and all of these I can make trapezoids. Okay? Well, no, not the tangent lines. Here's how we're going to, so let's review trapezoids a little bit. We are used to seeing trapezoids like this. So first of all, let me draw it this way. This is a trapezoid, right? This is an isosceles trapezoid. This is also a trapezoid. Okay? A trapezoid is defined as a shape that has exactly two parallel sides. So that's also a trapezoid. And when we draw that, what we have here is base 1 and base 2, right? The parallel sides are bases. And then the distance between the two parallel sides is the height. So here, that's the height. Now, the area is half times height times base 1 plus base 2. Okay, now, this is my trapezoid, all right? Now, what if I took the trapezoid and I drew it this way instead? Right? Same trapezoid, I now stand it up on that side. Now, again, the parallel sides, right? Base 1 and base 2 are these. The height is not defined as a vertical distance. The height is just the line that connects the two parallel lines. The line that connects the two bases is the height. So in this case, this is the height. Okay? And here, this is perpendicular. So now, area is still the same. Area is equal to h over 2, base 1 plus base 2. Now, if this is my trapezoid, now this height, this time the height, is the length of the subintervals.
That's the distance.
This is the length of the subintervals. And then base 1 and base 2, these are the heights. Or these are the y values. Let me just do it that way. Y values. Okay, so these are the y values. You have y1, y2. Okay? So now, if I have these trapezoids here, so suppose I have 1, 2, 3, 4, 5, 6, 7 trapezoids here. Okay? Or you know what? Let's do it simpler. So let's say we're gonna go from A to B like this. Not take the outer ones. We're going from A to B. Okay. This is my first trapezoid, right? Trapezoid number 1. This length is base 1. This is base 2. Okay? And then this is base 3, and then this is base 4, and so on and so forth. And then it's base 5, and then base 6. So now, how is my area going to look? So I have this first triangle, this first trapezoid. It's h over 2, base 1 plus base 2, plus the second one is h over 2. What are the bases for this one? Base 2 plus base 3. Do you see that? Plus, what about the next one, number 3? H over 2, base 4 plus base, base 3 plus base 4. Okay? Yeah. Yeah, there is. Give me a minute. Yeah. So, plus, what's next? H over 2, what's that fourth one? B4 plus B5 plus the very last one, H over 2, B5 plus B6. There is none. Hang on. Okay. So now, look at what happens. I can take out an H over 2, right? I can take out an H over 2. And then, look at the bases. I have 1 base 1 and 1 base 6. How many of each of the other ones do I have? 2. So it becomes very, very simple. I do H over 2, base 1, 2 of the ones in the middle, and then 1 of the last one. Okay, so that's the trapezoidal approximation method. There is no left or right. It's all the same. It doesn't make a difference because you do it along the curve. Okay? Yeah. Yeah.
So, my question is so let's say you're looking at that and you're saying that you wanted to start from the x-intercept as like your new A.
Mm-hmm.
So you started it like a little bit away from that. Would that mean that the first base is equal to, or the first height is equal to 0? Like let's say
no, it'll be like this one. Yeah, no, the height would be this. Because there would be a trapezoid there, like this. So it would be this height, and then that.
Not the origin, the x-intercept.
Oh. Yeah, well, yeah, it would be like f of that. F of whatever that point A is. Okay, yeah, it'll be f of A. Okay, so let's do this. So we're going to approximate the area under this from 1 to 5. From 1 to 5. With 4 subintervals of equal length. So 1, 2, 3, 4 subintervals of equal length, right? So the heights then are going to be 5 minus 1 over 4, 1 unit each. So that's what that looks like. Okay, now this is the height. So my area, and when it's a trapezoidal approximation, it's convention. You know, you can say T equals instead of A equals to know that it's a, it's like RM and so on. So it's going to be 1/2. Now for the bases. 1 over 2 because it's H over 2. It's it's half times the height.
Oh,
because the formula.
So you're timing it by the...
No. The formula for the area of a trapezoid is half times height times, yeah. I wouldn't, because then you forget at the end. Let's just go through and then I'll show you some shortcuts. Okay, so 1/2. So now for that first trapezoid, the first base is going to be f of 1. So that's 1 over 1 plus f of 2, 1 over 2. plus 1/2. I'm going to do it like one by one first, and then we'll do shortcuts. Now for the second one, it's going to be 1/2 plus 1/3. So f of each endpoint. Now for the plus 1/2, 1/3 plus 1/4. And then the last one, 1/2, 1/4 plus 1/5. Right? So do you see what I'm doing here? For each trapezoid, I'm evaluating each endpoint in f of x. Okay? Finally, when we plug it all in, it's 1.683. Okay?
Why are we using the
We're using both. So for this one, for this trapezoid, I'm using both. Okay? Yeah.
Why are we doing 1/?
Because the function was 1/x here. So I'm evaluating it's f of 1, which is 1/1. Then f of 2, which is 1/2. Then f of 3, which is 1/3. Okay. Partitioned into n subintervals of equal length. Okay, so here, so then to approximate, right, the area under the curve, this is what we were just talking about. You notice how we have h/2, right? We can take out the h/2 one time, okay, here. And then it's y of the first endpoint, okay, so f of the first endpoint plus 2 of each of the other endpoints, and then the last one. Okay, 1 of the last one. Okay? So what ends up happening, if you look at it a little bit more closely, if you have n subintervals of equal length, then the trapezoidal rule is the average of LRAM and RRAM. Okay? All right, so let's take a look at this one. Refer to the region R enclosed between the graph of the function. Oh, wait, there's, this should be between the graph of the function. I repeated this. Y equals, huh? No, it's not too important, but yeah, it's this one, because yeah. Okay, so here, because the function doesn't always increase linearly. If the functions were linear, then that would be true, but they're not. But this one is. Okay, so the y equals √2x from 0 to 8. So we're going to have to graph this one, right? This is why in pre-calc honors, I have to make sure that you can graph these without a calculator. So we're going to go from 0 to y equals 8. So at x equals 0, y is 0. At x equals 8, y is 4. Is that right? And this is a square root, so it's going to look like this. And so this region between the graph and the x-axis is called the region R. That's very common to label that region R. Okay, now we have 4 subintervals. So the height is going to equal 8 minus 0 over 4, 2. T. Now, so let me just do this. So each subinterval is 2. So we have a partition at 2, 4, 6. Okay? We have 4 regions here. So with the shortcut, here's how you're going to do it. T is going to be height divided by 2 times, okay? Times f of 0, all right, f of 0 is root 2 times 0 plus these middle ones, the middle purple ones, we're going to take 2 of each. So 2 times f of 2 plus 2 times f of 4 plus 2 times f of 6. And then the last one, we only take 1. Okay? And then, so finally, t is 20.585. Right? So do you see how this is consistent with what we did before? We have 1 y naught. These 2 y1 plus 2 y2 plus 2 y3, and then 1 y4. Questions? All right, let's do another one. Now the region R is between the function negative x squared plus 4 and the x-axis from 0 to 2. So negative x squared plus 4 has a y-intercept of 4. And then we're going from 0 to 2. At x equals 2, how much is y? 0. Okay? Okay, so let's see. How many subintervals? 4 subintervals. So it's going to be 2 minus 0 over 4. That's my h. Each is a half. So here's how we're going to partition it. Okay? So we're at a half, 1, 3 over 2. So t is equal to 1/2, okay, h over 2. I know we can do 1/4. I'm just, covering all my bases here. Times, okay, 1 y0. So 1 times f of 0. So negative 0 squared plus 4. 2 times all the rest. So 2 times negative half squared plus 4. Please get the negative right here, right? So this is going to be, even if you don't have a calculator, this is going to be negative 1/4 plus 4, okay? And then 2 times the function evaluated at 1, negative 1 squared plus 4. 2 times negative 3 over 2 squared plus 4. And then 1 evaluated at 4. 2. Okay. And all that is 5.25. Okay, just like with RAM, we could do the same thing here with a table. All right, so use the function values in the following table and the trapezoidal rule with n equals 5 to approximate the area under the curve from 0 to 5. So n equals 5, and then you see here, these x values are your heights, right? So here you have a height of 1, and it continues through. So here's the main difference between LRAM, or the rectangular, and the trapezoidal, where these are your heights, and these are the bases. But, generally speaking, everything else is the same. So, same situation. T is height 1 divided by 2. These are your y0, y1, y2, yn. So same situation. We take 1 of the first and of the last, 2 of everything inside. You could, so you can even do it, you know, this way. 2 times 16, 18, 20, 14, if you want to save some lead, plus 10. Okay? $78. Okay. What's the issue here? Number 5. Yeah. Right. The subintervals are not of equal length. And nobody said that in a trapezoidal approximation, the subintervals have to be of equal length. Okay? You could, you know, you could be a rebel and do this. It's fine. So here I have my height equal to 2, then 1, then 3, 2, 2. So those are all your heights, and then these are going to be the bases. So T equals. Now this one, I can't collect h over 2 outside, right? I have to do each one separately. So for the first trapezoid, it's going to be 2 over 2, 5 plus 6. Then 1 over 2, 6 plus 11. Then 3 over 2, 11 plus 15. 2 over 2, 15 plus 12. 2 over 2, 12 plus 10. You can, but it's more work than it's worth. 107.5. Because it's h divided by 2. Trapezoid, area of a trapezoid is 1/2 times base 1 plus base 2 times height. Okay, here we go. An observer measures an outside temperature every hour from noon to midnight, recording temperatures in the following table. What was the average temperature for the 12-hour period? Okay, average temperature. Okay. If they were, no. I'll talk about it. So here at noon, T equals 0. Okay. Here, T equals 12, right? What's H here? 1. All right, so go ahead and let's find T here. So it's going to be 1 over 2, and then the sum. So here, we're going to get 782. What have we gotten here? What are the units here?
No, it's time times temperature, which is hours.
No, what have we, okay, so what did we, okay. So what did we do? We had, this is the temperature, I'm sorry, this is the time. And then this was the temperature, right? When I found my area, I multiplied the height by the base. So if this had a unit of hours, this has a unit of degrees Fahrenheit. The units here are degrees Fahrenheit times hours. What am I looking for though? I'm looking for the average temperature, which should be in degrees. So what should I do to this? What should I divide by to get rid of those hours so it's just in degrees? I need to divide by a time unit. And if it's the average that I'm looking for, then, you know, that's what I need to do. So the average is 782 over 12, which is approximately 65.167. Now, as far as just adding them up and dividing by 12, that when you do that, you can do that with tests because you have distinct test scores. Your tests are not a continuum over the whole semester. But this temperature here is a continuum. When you graph the temperatures, right, it should be like the curve should look like that. They are not distinct data points. So in order to account for that continuity, then this is I'm answering your question. In order to account for that continuity, we have to do it this way. Otherwise, if you just add up the distinct points and divide by 12, it's like test scores. It's like the world only existed on these like once an hour. Okay? Yeah, it's a continue. Right, exactly. It doesn't account for the continuity. Okay, that's discrete math. This is continuous math. Yeah. There are 13 hours, but 12 subintervals. So you divide by 12 because like each one of these is one subinterval, right? 1, 2, 3, 4, 5. If you look at the trapezoid here, there are 1, 2, 3, 4 trapezoids, but how many points? 5. I know. It's like magic. It's like one of those illusions, right? Where you're like, it's like they hypnotize you and you count to 10 but get 11. Have you seen those?
Yes.
They hypnotize people and like they make them like forget about the number 4 and they're like, how many fingers do you have? 10. And they're like, count your fingers, and they're like, they don't know 4, so they go 1, 2, 3, 5, and then they end up with 11. And like it's all so confusing. And then they're like, wait, but I'm supposed to have 10 fingers. How did I get another finger? Okay. This one. The table below records the velocity of a car in miles per hour at different time intervals. I feel like I have to underline miles per hour. At different time intervals over 20 seconds, right? Already a discrepancy in units, okay? Use trapezoids to approximate the total distance traveled and the average velocity. Note the difference in units, okay? You know that's not going to say that on the test, right? Note the difference in units, right? Okay. Okie dokie. So, we have time. That's the x-axis. These are the heights. We have the velocity. These are the bases. That's the dependent variable, okay? So now, are these equal subintervals? No, it's jumping up and down. So T is, the first one is 3 over 2, 13 plus 27, plus, all right, go ahead and do this. I'm going to race you to it and then find the answer for me. Okay, what did you get for T? Anybody? Okay, wait, don't call it out then. Okay, so it's 8:58 for this one. Oh, this is what it's, okay. So it's 8:58 for that one. Let's So you have, yeah, let's convert it. So if you do 858 divided by 3,600. So the thing is, one is in hours, one is in seconds, right? Then it's 0.2383 miles per hour, right? The car is being driven in miles per hour, so convert it to miles per hour. Okay? So the total distance traveled is 0.2383 miles. All right? That is a tiny, tiny number, or it's 1,258.4 feet. We know how the conversion is. We talked about it last time, 5,280 feet. And then, so the average velocity, again, you would just, add and divide if it was like, driving and stopping, you know what I mean? But it's not this, it's continuous. It's a continuous function. Average velocity is 858 all over 20, 42.9 miles per hour. Okay, homework for this is another worksheet due Wednesday. Tomorrow? Do I see them? Oh yeah, when? Tomorrow. Oh my gosh.